do it. The general version of this, especially for the bosons, is quite complicated and not really worth learning. I can tell you this, anything I give you on a test or quiz will be something where you can easily, in the time allotted, write out all combinations. Like, it'll be fewer than this. Okay. But the more I can give you more, it's fun.
The multiply, the odds is getting better.
I love writing out numbers. You can write a program to do it too. It'd be good programming practice. But it's not hard to do by hand. It's actually not that easy to do in a program, by the way. It's doable. It's not that hard, but like it's not as simple as you might hope. Okay. Good. Next. Let's talk about something else. This one is a little bit kind of like either here or there. It's kind of a random topic, but it's an important one. People care about it, so we'll talk about it. And that is something called.
Where's square root?
Oh my god.
Entanglement. Okay.
Oh.
I don't need this in my life.
Yes, you do. Quantum tunneling, let's go.
It actually might be very, very important.
Quantum tunneling is not.
I don't use it.
Quantum tunneling is not that important.
So let's say you have a neutral pion, for example. The neutral pion is going to be K, right?
Base hole.
Kaon. Neutral kaon. Wait, what was that K? No. Whatever. Just pretend it's neutral pion. I know this is not the right K mode, but like, so it's going to be. And it has a spin of 0, because they do have spin 0. Okay? Now, it breaks into 2 particles. Just for simplicity, let's make it an electron and a positron. Okay? They don't really do that, but let's just say they do. Okay. We know that electrons and positons both have spin what? 1/2. Good. They both have spin 1/2, right? Remember that one? We're supposed to learn that. Okay, so they both have spin 1/2. All right. Well, that's good. What can you tell me about their m values, right? Remember that if the possible m values are what? 1/2 and -1/2. But remember that angular momentum has to be conserved. Angular momentum has to be conserved. And so, what can you tell me, therefore, about these m values? They'll have to add up to 0, which means they'll have to be in opposite directions, right? So one's this way, the other's this way, so that you add up to 0, right? Okay, good. Which one's up and which one's down? I don't know, right? It could be either one, right? Okay, good. So the wave function of these, right, can be written like this. Either this one's up and this one's down, or this one's down and that one's up, right? And it turns out there's a minus sign between them. Don't worry about that part. Because I told you not to worry about it. We don't have time to teach you that. Sorry. So this is the wave function of the system. Okay. Now, what that means is because of the conservation of angular momentum, you don't know the spin of the particles. But if you measure this one and it's spin up, then what do you know about this one? It has to be spin down, right? There is no alternative because you know angular momentum has to be conserved. So because of that, when you collapse the wave function of this one with the measurement, you also collapse the wave function of this one. And that makes them entangled, right? Entanglement means that measuring this one also gives you a measurement of this one. And so their wave functions are not independent. They are entangled with each other. They're in an entangled state, they say. Okay? Because measuring one gives you measurement of the other. Okay? So that's neat, right? So the next argument is an argument due to Einstein, very famously. Einstein, Polensky, and Rosen brought forth this argument. They usually refer to it as the EPR paradox. But it's not a paradox. It's just an argument. They didn't call it a paradox. It's an argument by Einstein, Polensky, and Rosen, or EPR. And here's how it goes. Take this positron and go to the other side of the universe. Okay? I don't know how far that is exactly, but let's say it's pretty darn far. Okay? Like, you're like, what if the universe doesn't have another side? We'll bring it far away. Okay, like how far away? I don't know, 1 million light years, okay? Could you do that? Well, it would take a while, like more than 1 million years, right? But you could do it. I mean, eventually. So get it really, really far away. Okay, the other electron stays at Earth. This one goes really, really far away. Okay, now what? Well, I measure this one. And what does that do? It collapses the wave function. For which particle? For both of them. Here's the question. If I measure this one here, right, when does the wave function of this one collapse?
Oh no.
Instantaneously?
Yeah.
Don't do that. Simultaneously
When
is
it's
relative.
1 million light years away?
Yes.
No.
What does that mean? Signals can
So,
travel faster than the speed of light. Everything in my life.
So,
That's
is that what do you think?
It's such a pain in the butt. Yeah.
Maybe there's a speed of light delay, but wait a minute, if there's a speed of light delay, then while that speed of light thing is going, what could you do? You could measure this one, and if you got something contradictory, then no, you can't get something contradictory, we already know that.
But then if it sends a signal back in order for you to register it on Earth.
So, we have an issue here. All right, now, here's the thing. You can, yeah, it has to happen instantaneously. Because otherwise, while the thing was traveling, you could measure this one, and that would allow you to get an inconsistent result, and you can't do that. Okay? So therefore, the wave function collapse has to happen instantaneously across the universe. Does that seem like a problem?
Yeah.
Well, it's not actually a problem for relativity. Okay? And Einstein knew that right away. Because you can measure this thing to be spin up, but you have no way to make this thing spin up. Right? In other words, I can measure it and know that this one is spin down, but I have no way of changing this one to spin down so that I can use it to send a signal. Okay? So this mechanism is weird, but it does not allow you to send a signal. So that is not the problem. It does not break relativity.
That means that it's like an issue of sounding maybe like any one reference frame or the other.
However you work it out, it's still fine. It's true that it could be that the question of when the wave function collapse becomes very ambiguous in different reference frames, but you get no physically inconsistent results. In other words, so you're saying measure this one and then measure this one, and then another reference frame you measure in opposite orders, right?
Yeah.
But you still get physically consistent results either way, so it doesn't really affect anything.
So then doing that, how can you say that once it's turned together, it's already going to do that?
Well, it's like I said, it still gives you physically consistent results either way, right? It doesn't form a paradox. It doesn't form a paradox, it's just weird. Well, they decided when, so when the wave function collapses becomes ambiguous, but there's nothing physically measurable that changes about it. No, they're not guaranteed to decide. It's still random. There's no way to send a signal from one to the other to predict the other. Or if it is, then you break anything interesting about it. It's like space-like.
I mean, like, if you measured one and it's choosing randomly, then couldn't they choose? Why wouldn't they choose different things for each choosing randomly and each choosing first?
Because they're not. When one first one measures, then it collapses the wave function. The other one's not random. And if this one measures first, then it collapses the wave function. The other one's not random.
But the results stay the same.
The result's still the same. So there's no paradox. It's just weird. Yeah.
I have two questions.
Okay.
So with the wave function change when you're looking at different reference frames, then like if the possibilities aren't 50-50 for like a certain thing?
We try not to think about it too much. The answer is I don't want to answer that question. I don't even know the answer. It's really hard. Relativist quantum mechanics is really hard.
And then for when they collide, or when they like the particles like go off, do they already have this like spin, or is that still not?
No, it's a wave function, right? So it's whether one's up. Well, actually, we'll talk about this like right now. But, well, we'll talk about this. That's a very good question. We'll do it right now with the native question.
Yeah. So basically, what you're saying is that like your knowledge doesn't cause the event, you're not the same.
No, we're not saying that. What I'm saying is that you cannot use your knowledge here to send any signal over here, right? I can know that this will be spin down, but I have no way to change that, right? So there's no actual transmission happening. It's just a sort of knowledge of something across the universe, but not an actual signal. So it doesn't break relativity, and Einstein doesn't do that. But what he does do is it posits the existence of some physical effect, wave function collapse, that goes faster than light, that violates relativity, and it doesn't break relativity, right? But it's kind of weird to make that claim, right? Einstein refers to this effect as spooky action at a distance. It sounds better in German.
What? What is it in German?
Einstein uses that phrase, I don't know German. Einstein uses that phrase derisively. That's why it says spooky. Because Einstein says that this can be compared to what Emily was just saying. Look, so Einstein says, here's what the Copenhagen interpretation, the way we've been talking about it, right? It says that when you choose this, it collapses the wave function, and mysteriously, this weird kind of other, not quite forced thing sends across the universe instantly everywhere in space, violating every principle that applies to every other physics effect we know, right? And instantly causes the wave function to collapse over here. And so you have to posit the existence of this spooky action at a distance. Einstein argues, and Polonsky and Rosen, they argue that there's a much simpler explanation, which is what Emily said, which is it was spin up and spin down all along. We just didn't know. And when you look, you're like, oh, it's spin up. That other one's spin down. There you go. Right? That is called a hidden variable. Hidden variable means it has an answer, we just don't know it. It's hidden. Right? And so Einstein came down and said hidden variables make more sense. The Copenhagen interpretation relies on this spooky action at a distance, a weird speed of light effect, faster than light effect, that doesn't violate relativity, but you have to imagine this extra, you have to add in an extra faster than light effect. And Einstein's like, you don't need to add it in, just assume there's something we don't know about it. Okay, here's the interesting part. When this first came out, people were like, oh, that's interesting. And they argued a bit about it, but they're like, well, you can't really settle this, right? Because before you make a measurement, you don't know what happens. The outcome is the same either way. And Einstein, remember, is one of the fathers of quantum mechanics. He developed a lot of it. The math was all fine. The predictions were all fine. He just disagreed about the philosophical underlying meaning of what was happening. So the fun part is later, well, much later, after Einstein and Bohr and all those guys that were dead, there was a man named John Bell who came up with what's now called Bell's theorem. And Bell's theorem actually showed a way where you could experimentally distinguish between these two predictions. He found that there was a particular setup you could make that gave one answer for hidden variables and a different answer for the spooky action at a distance version. And so he actually found an experimental way to determine it. It turns out it's not just philosophical. It wasn't easy to come up with, but he came up with it. Basically, there's a probability you could measure, and the probability has to be less than a certain value for these theories and greater than that value for these theories. The value's like 0.7 something. And then, at the time, people were like, well, that's nice, but there's no way to measure it. We can't control like individual electrons at the time. But about 10 years later, our rapid advances in microtechnology, now they call it nanotechnology, allowed for really much better control of these things. And we were able to make our first test of Bell's theorem. They've done repeated tests getting better and better. The key test is one that makes it, the key is you basically have to release these particles and then have the detectors that are detecting them change direction while the particles are in flight. And the best version of it is one that the detectors are far enough apart that they can change direction fast enough that light could not make it from one to the other. So there's no possibility of any signal. And they had that set up, and what the Bell's theorem detectors found, conclusively, all of them found the same thing, is that, apparently there is, in fact, this spooky action at a distance. And Einstein may have meant it derisively, but that's basically how it works. We measured it out experimentally. Now, it is not the only possible interpretation of the experiments, but it does remove the simplest, most obvious form of hidden variable theory, which is called local hidden variables. That is, say that a particle knows its own spin, and we just didn't know it beforehand. It is experimentally disproven by the Bell's theorem experiments. And so the only, there are other ones that are global hidden variable theories and other ones that don't go by the wave function collapse method. But I mean, basically this one works. This one works best, which is why I teach it to you. Yes, sir?
Why would the spin fail to add up to 0 after like 0 left
Because conservation of angular momentum. If nothing else is attached to them, if nothing else has affected them,
But you
No. We don't do anything to them except move them, and then you measure it. That's it.
What was the experiment that was like?
Oh yeah, no, so they do something like this, but they change the direction that you're measuring in. Because you can measure in the Z direction or the Y direction or the X direction. So you make the detectors change which direction they're measuring mid-flight. That's the key to Bell's experiments, yeah.
So this is for maintaining conservation of angular momentum. What if you have two fermions that can't be in the same state of stream? Would the same effect happen?
You can basically do this with any conservation law, okay? Which includes any like physical law, right? Which includes Pauli exclusion and so forth, right? That they'll cause entanglement. You can even get like partially entangled particles where you where if you measure one, you know something about the other one, but not 100%, and things like that. So it all comes out of the math. So if the math requires that it be this way, then it's entangled. So any physical law you come up with, you can set it up. You can do it with momentum. You can probably do it with Pauli exclusion, probably some way. Here there are different states because they have different spins, so it's no big deal. But they're also different positions, so it's not that big a deal anyway. Okay, so this indicates that there's this. So quantum entanglement now is a well-established procedure. In fact, now we can exploit it because here's the thing: you cannot use it to send a faster than light signal, which is good because we don't want to send faster than light signals, right? Because what would be the problem then? Because then we can put one thing at the beginning of the train and the other thing at the end of the train, and then oh man, stupid paradox doesn't work anymore. So it's good that you can't violate the speed of light with this, but you can do some things that you wouldn't be able to. Let me give you a simple example. Suppose you're invading a galaxy. You guys do that sometimes, right? Yeah. And like you're invading a galaxy with one of your friends, right? So you're gonna do like a pincer attack on them, right? Okay. So you go to like the opposite ends of the galaxy to start your pincer attack, right? You guys got a lot of free time, like a few billion years. And so you go to the opposite ends of the galaxy to start your pincer attack on them, right? Now the people defending the galaxy are going to defend too. So let's imagine you have two like attack options, A and B, right? Like two different strategies you could use, strategy A and strategy B. But the defending guys could also defend against strategy A or strategy B. So you really don't want them to know which one you're using, right? Otherwise they can prepare for it and you wouldn't be able to successfully invade. So here's the thing though, you're attacking from opposite ends of the galaxy. If you sent a signal from yourself to your friend, then not only would it take a long time, but aside from that, also that signal could be intercepted, right? And then they would know which one you're using and then be all over it, right? So here's an uninterceptable way of doing it. You take that you guys start before you split up to go to opposite ends of the galaxy. You guys start and you each take one entangled electron. Like I get one and you get one. And then you go off to opposite ends of the galaxy, right? And then, in a predetermined way, you look at the electron at some predetermined date, right? And you look at it, and you just decide in advance. If mine is spin up and yours is spin down, then we're doing plan A. If mine is spin down and yours is spin up, then we're doing plan B, right? And you can look at it and be like, aha, plan A, right? And you know that he's going to see the same thing and choose plan A as well. And you're going to coordinate the plan A together without sending any signal. I mean, galaxies are big. I just want something that show you can do it faster than light.
What if they detect the spooky action at a distance?
What?
What if they detect the spooky action at a distance?
You cannot detect the spooky action at a distance, to our knowledge. Yes?
Isn't it just the same as like predetermining which plan you're going to do before you execute it?
No, because see, the spies could find out your plan beforehand. So here, you don't determine the plan until right at that second, right? But you know the other person is to choose the same plan.
I don't think you guys.
It's actually something that cannot be done classically because of the speed of light limit. Well, the spies look at the electron, they'll break the entanglement, and so you got to keep them away from that. But I didn't say it was foolproof in every way. You have a question?
What did you say?
That's still fine because, well, here's the other thing. The spies need time to transmit their information, right? Because of the speed of light, right? So as long as you can keep the electron undisturbed, right? Then when you look at it, you will be the first person in the universe to know that information. Well, you and your friend both, right? And no one could have got to it earlier. And by then, if the spies find out, it'll be too late.
Observation costs wave function. I look at it, right?
Right.
What's the difference between a collapsing to A or collapsing to B?
Right, the spies could always find that. Yeah, I know. this is an example, but there's a difference, right? With the upper here's the difference. You can break the entanglement, and once you measure it, the entanglement's gone, right? And this is the key to called quantum cryptography. Quantum cryptography works on just this principle, where you take an entangled electron or a photon usually, and get sent it to the other person. And the way it works is, if they're in entangled states, then you measure a bunch of them. You put like a check signal. And if they're in entangled states, when you measure it, you should get certain probabilities coming through. Okay? But if someone is intercepting the states and then looking at them, what happens when they look at them? Then they collapse the wave function. When they collapse the wave function, the entanglement is gone. When the entanglement is gone, you on your end get garbage information because the entanglement's broken, right? So basically, what you do is you send out you periodically send out like a signal that's like, here, check to make sure you get this answer right. And you should get it 100% right because you're lining it up, you're getting the entanglement, it should be 100%. But if someone interferes, the entanglement's broken and you basically get random spins after this point. And so because of that, when they pass it along, the lack of entanglement will give you garbage answers and it won't line up. And you're like, oh, someone's eavesdropping on this line. And so it's a way in which you can know for sure. And you're like, well, what if they just put it aside and don't look at it? But they can't, because first of all, it has to go through, right? And there's an important theorem in quantum mechanics called the no-clone theorem, which says that you can't clone any quantum state. It's not possible. And so,
unless you try really hard.
You can't so quantum cryptography is in principle not interceptable, although there's no such thing as really not interceptable. You said if you had a different way to do it, just bribe the guy, right? On the flip side of this is quantum computing. Quantum computers use entangled states to do many operations at once. They're not actually as fast as they sound, but they allow for the implementation of a few very specialized algorithms, such as Shor's algorithm, which is used to factor large primes. The product of two large prime numbers, like 15 is the product of 3 and 5. Pretty good, huh? Shor's algorithm is important because that's the principle behind all RSA encryption, which is what all of your internet encryption is based on. It's based on the fact that taking the product of two very large prime numbers is virtually impossible for a computer to factor. It has to guess and check, and there's too many things to guess. It will take years for a computer to crack these things, many, many years for a current computer to crack them. So, but Shor's algorithm can crack it very fast, like in minutes. And so, if someone has a quantum computer which is sufficiently large, has to be very large, to implement Shor's algorithm, then they can break all their internet encryption and read anything they want. And I was at a panel at a conference. We remember that conference I was at in just a few days. There was a panel there on quantum computing, which is really interesting. All these people working at the Naval Research Lab. And someone said, what do you think is the time scale on this? And this guy says, I think the Chinese are way ahead of us. And he says, my expectation is they should have a factoring computer, a Shor's algorithm capable computer, running within 5 years if they don't already have one. And I'm like, oh, that's good. So,
is that what you said?
Guys. When they take over the world, it'll be handy to know.
I have family in China.
How long will it take the signal to reach us?
You guys have a great Thanksgiving. Remember, if you want to make any changes on Sunday, that's